Here we have one more example that is an equilibrium problem. So Romeo, we have a ladder, leans it against the wall. We have the mass of the ladder, and how far it is from the wall. We have Romeo's mass. We're told he gets 90% of the way to the top, and that's when the ladder begins to slip. We want to find the coefficient of static friction between the ground and the ladder. So I'm going to draw a rough little sketch here. So the ladder is right here. We know the length of the ladder is 10 meters. We know the mass. I'm going to call this M sub L, the mass of the ladder. And we know it is located 2.8 meters from the wall. All right, they're telling us that the wall of the Capulet residence is frictionless. So we can go ahead and assume we only have a normal force from the wall. There's no friction there, or we're assuming it's frictionless anyway. Now with equilibrium problems, anytime we're trying to relate anything in equilibrium, we need to draw the free body diagram. Here we're going to draw the free body diagram of the ladder, because that's what Romeo is going to be standing on, that's what he's going to be climbing to get to the window, and that's what the force of friction is acting on. So I have the wall's normal force. I know the ground is pushing upwards with the normal force. I'll call that one just N, whereas N sub W is the normal force with the wall. We know the ladder itself, we're going to put, because they tell us it's a uniform ladder, that means we can say the force of gravity acting on the ladder because of its own mass is acting exactly in the middle. And then Romeo is going to be standing on the ladder, so mass of Romeo times G. Then they're asking us for the coefficient of static friction. So there has to be friction that's not allowing the ladder to slide. So the force of static friction to keep the ladder from sliding away from the house is going to point towards the house. All right, let me draw this bigger. I'm just going to draw what I'm representing the ladder. So the normal force with the ground, the force of static friction, the force of gravity because of the ladder's mass, the force of gravity because of Romeo's mass, and the normal force with the wall. All right, so ultimately to find the coefficient of static friction, that's going to come from the force of static friction. So mu times N, and specifically N with the ground, because that is where the friction is acting. So it needs the normal force at the same location. All right, so if I want the force of static friction, and we can talk about torque, we know torque is RF sine phi, meaning R times F perpendicular. We need to take the torque around some sort of rotation axis. And as I've mentioned before, I recommend putting your rotation axis at the location where you have the most unknown forces. In that case, that means the rotation axis would be put at the bottom. But by putting the rotation axis there will be no torque around that axis due to this friction. and there will be no torque due to this normal force. And that's because R is 0. That's the same as trying to push on the hinges of a door to get it to open or shut. So that's going to take the force of static friction out of the torque equation. We will have a torque due to the weight of the ladder itself, a torque due to Romeo, and a torque due to the wall. The only force we wouldn't know is this normal force with the wall, and so our torque equation will allow us to solve for that. Now we could put the rotation axis at the top, but that would require us to calculate the torque due to friction and the torque due to the normal force with the ground. I'll walk through that at the end, just in case you're interested in seeing that. For now, I am going to set up the equation that describes the net torque around the floor. So as we've mentioned, we have the torque due to Romeo. We have the torque due to the ladder. Both of these would tend to rotate the ladder counterclockwise. The torque due to the wall would tend to rotate the ladder clockwise. So we're saying the net torque needs to be 0. I'm just jumping this step. Torque due to Romeo and the ladder being positive, we would subtract the torque due to the wall, set them equal to 0. So I was just jumping that step. The torques that would cause counterclockwise motion need to balance out with the torques that would cause clockwise motion. All right, so let's look at these individual torques. We will need to know an angle of some sort. Let's go ahead and set this up symbolically first. For Romeo, R, the lever arm for Romeo, times the mg for Romeo, times the sine of, I'll call this phi 1. It will specifically be the angle between the ladder and mg. And that's because whenever we draw in R, we start at the rotation axis and keep going until we get to the location where the force, in this case, the force of gravity due to Romeo, is applied. So this means R of Romeo. We're told that he gets 90% of the way to the top. So that's 0.9 times the total length of the ladder. So let's do this. 0.9 times the length of the ladder. The ladder's 10 meters. So 9 meters. I'll put that in. 9 meters is how far up when the ladder just barely starts to slip. So just the point after our maximum friction. The mass of Romeo, we're told, is 70 kilograms. G is 9.8. We need to figure out that angle, phi 1. The way we can do that is we know the ladder is 10 meters long. And we're told that it is placed 2.8 meters from the wall. So the phi 1 up here, let's see, I have opposite side and hypotenuse. I can say that the sine of phi 1 will be 2.8 over 10. Technically, we could just plug that whole thing, that ratio in if we wanted, since we have sine of phi 1 in our equation. I will go ahead and find the angle, because I know that might be helpful for some of you. So inverse sine of 2.8 over 10 tells me that phi 1 is 16.26 degrees. Now again, if we come back to the force, this mg can be thought of as having a component of force parallel to the ladder and perpendicular to the ladder. This perpendicular piece can be drawn over here, and that's why we get mg sine of that angle as the perpendicular piece. It's only forces that are perpendicular to the lever arm, to the ladder in this case, that would make it rotate. Okay, so the torque due to the ladder itself, similarly, the R, the lever arm from the rotation axis out to the ladder, times the force, the mg of the ladder itself, and then sine of the angle between the ladder and mg, which is actually going to be the same as it was for Romeo, because we have the same setup. Now, the angle, I mean, not R, because R points from the rotation axis up to where the force is applied. So R of the ladder is exactly half the length of the ladder, so 5 meters. And again, that's because the problem tells us it is a uniform ladder, so essentially telling us that the force of gravity acts at the middle, the geometric center. So if we plug these numbers in, 5 meters, the mass of the ladder, 22 kilograms, G, 9.8, sine of the same angle. This needs to equal the torque due to the wall, the normal force with the wall. So R for that force times the sine, this is a theta 2, because I need the angle up here between, R would be along the ladder, so R for the wall is the whole ladder, 10 meters, but the force is perpendicular to the wall, so this is what I mean by phi 2. In our equation, RF sine phi is always the angle between the lever arm vector, the one that points from the rotation axis to the force, and then the force. Okay, well, phi 2 is going to be 90 minus the 16.26, because it's the angle down here with the ground. So 73.74 degrees. So we can come up here, just gonna move it slightly. R is the entire length of the ladder. We don't know this force, so I'm gonna leave it as N with the wall, times the sine, the angle between the lever arm and the force is the 73. So this allows us to solve for the normal force that the wall is exerting on the ladder. So let me plug these numbers in. Oh, that was the wrong number. Dang it. Okay. Getting 211.51. Now again, I'm not at a final answer, which is why I'm not fully rounding yet. And I guess I can't technically have the 1, because this answer cannot have more sig figs than these intermediate angles I rounded to. Okay. Normal force with the wall is what we have now calculated. But we need to figure out the friction force because we're trying to get to a coefficient of friction. So that's where we're going to come back and look at the net force in the x direction being 0 and the net force in the y direction being 0. In the x direction, going back to our free body diagram, we see the normal force the wall is exerting points to the right, friction points to the left. Those are the only forces in the x direction, so they must add up to be 0, meaning our force of static friction has to equal this force we just calculated that the wall is exerting. So we can say the coefficient of friction times the normal force with the ground, not with the wall. So as I mentioned earlier, when we say the force of static friction is mu times n, that n has to be the normal force with whatever surface we're talking about the friction with. This has to equal 211.5 newtons. So we can solve for mu sub s if we figure out what the normal force is with the ground. And that will come from looking at the forces in the y direction specifically. So coming back to our free body diagram, we have the mass of Romeo times g. So the weight of Romeo downwards. We have the weight of the ladder itself downwards. And then we have the normal force equal to 0. You may have very quickly just jumped to the normal force has to equal the weight of Romeo and the weight of the ladder combined. So let's see, Romeo is 70 kilograms, ladder is 22. Multiply that by 9.8. We find that the normal force, 901.6 newtons. So coming back to our equation on the left, I'm getting 0.23. And I think, yeah, we have at best 2 sig figs. Now, since it told us this 90% of the way up the ladder is when the ladder just barely starts to slip, we could probably say that mu sub s, or we should say mu sub s is just barely less than this value. Now, by barely, I don't really have a good answer for that. We could say something like it's 0.22, something along those lines. But it has to be close to the 0.23, but not exactly equal, because the ladder was slipping at that point. Okay. Free body diagram, draw the forces. Let me show you this setup really quickly. Had we taken the torque around the other end. So normal force with the ground, friction, the mg of the ladder, the mg of Romeo, and the normal force with the wall. If we had placed the rotation axis at this top corner, which is totally valid, we would need to say the torque due to the ladder plus the torque due to Romeo. Let's see, those would both rotate the ladder clockwise. So this way, this way. The friction would also cause clockwise rotation. So the torque due to friction needing to equal the torque due to the normal force with the ground. The R's would have different meanings as well. So when we say torque is RF, oh, my computer's freezing up a little bit again. RF perpendicular or RF sine phi, whichever way we want to write it. R, for example, for Romeo would be from that top of the ladder down to the force of Romeo. So the torque due to Romeo would be 10% the length of the ladder, right? If Romeo walked 90% up the ladder, then he's a tenth from the top. Mass of the Romeo times g. And then we need the sine of the angle between them. Now, the sine of this bigger angle gives us the same answer as the sine of the angle between them. So phi 1 that I drew before, if I call this phi 3, for example, the sine of phi 1, the 16.26, gives me the same answer as the sine of phi 3, 180 minus phi 1. So whether we use the angle phi 3 or phi 1, it works just fine. The torque due to the ladder, the lever arm still points down, so starting at the top of the ladder, because that's where I put the rotation axis, and go down to the middle of the ladder. The length of that lever arm is still half the length of the ladder. The force is still mass of the ladder times g, and then again sine of phi to get those perpendicular components. The torque due to friction, so just side note, these are the terms that would go in to our net torque equation. The torque due to friction, the lever arm points from that top of the ladder all the way to the bottom. So the length of that is L. The force would be the force of static friction. And then we would need the sine of phi 2 to get the perpendicular component. This would go in there. Finally, we would have to account for the torque due to the normal force with the ground. That normal force has a component that is perpendicular to that ladder. This normal force can be thought of as having this perpendicular component to the ladder. And that's why we would have to account for the torque. The length of the lever arm is L. It has the same lever arm as the friction force. The force would be N. And then we would need the sine of phi 1, because that would be the angle between those. So this would need to go in there. This would be a little more involved because we don't know the force of static friction, nor do we know the normal force, which we could totally put in mu times n, but that still leaves us with mu as an unknown and n as an unknown. And so we would need to use the net force in the y direction that we've talked about before previously. The normal force, adding the forces in the y direction, that normal force with the ground would need to balance out the weight of both the ladder and Romeo. And so we would need to substitute this in to our torque equation, and then we could find mu, which is fine. It's just a couple more steps maybe than what we did before. So there's no problem with that. But typically, if students try to put the rotation axis at the top, they forget and don't account for the normal force creating a torque. So that's why I wanted to mention it. All right, one other thing I want to mention really quick. When we talk about torque being, let me draw my picture one more time. When we say torque is RF perpendicular, it can be the R that's perpendicular to F as well. What I mean by that, let me get some forces written in here again. M ladder G and Romeo G. So for example, the torque due to the normal force. If we think in terms of distances, the problem told us that the ladder was placed 2.8 meters from the wall. The distance, if I imagine just making my normal force nice and long, and then I come and put my rotation axis at the top, and just draw a line from the rotation axis that meets that line that represents the normal force at a right angle, these are perpendicular. This horizontal distance is perpendicular to this normal force. We can say that the torque created by the normal force is that horizontal distance times the force. It's 2.8 times the normal force. Before, just previously, we said we ended up with the normal force as the total distance and 10 times the normal force times the sine of our angle. And our angle, phi1, was the 16.26 degrees. 10 times the sine of 16.26 is, if I kept all my digits, it is 2.8 times n. So whenever we're taking the sine, when we write out torque is RF sine phi, where phi is the angle between R and F, it's just finding the component for us that's perpendicular. If we can look at a picture and find the distance that is perpendicular, so for example, MG, I could draw a line straight up. The distance from the rotation axis to that point, X for Romeo, would be 0.1 of the total X of 2.8. So we could say the torque due to Romeo is not only 0.1 times the entire length times the mg of Romeo times the sine of 16.26, we can say that it's 0.1 times 2.8. This is the perpendicular distance times mass of Romeo g. It's a lot to think about, for sure. But again, the process of the cross product is to multiply perpendicular components. For those that end up taking statics, if you can find the perpendicular distance, sometimes that's the easiest way to go. But this RF sine phi also works as long as you know the angle between the lever arm vector and the phi vector. one other case would be the torque due to friction here. If I extend out the friction force, I just need to extend it in whichever direction so that I can draw a line from the rotation axis that would intersect that force at a right angle specifically. The torque due to the force of friction would be that y distance times the force of static friction. So sometimes it ends up being fairly straightforward to find the perpendicular distance. Sometimes we need to find those components, which is what our equation does for us, as long as we are careful about finding phi, the angle between R and F.